In this video, we are going to cover a worked example of Dijkstra's shortest path algorithm. So for a Dijkstra's shortest path algorithm, we take as input a graph. So our function might look like something like Dijkstra, compute or whatever, that takes in a graph and a source vertex. So it could be an integer or it could be just a string label or some label that describes the vertex. And this should return the shortest path from the source to every other vertex in the graph. So let's say for this particular graph, if I pass in the source as 0, the program output or the algorithm should give me back all the shortest paths between 0 and 1, and then 0 and 2, what's the shortest path between 0 and 3, and 0 and 4, and so on. The two constraints for this algorithm include, the first one is that the edges must be non-negative. The weights of the edges should be non-negative. So in this case, all the edges have non-negative weights, as you can see in the graph on the right. The second constraint is that all the edges should be directed, or the graph should be directed. So we have a directed graph, as you can see in our worked example. So how this algorithm works is we specify the source vertex S, and to compute the shortest path between the source and every other vertex, we need 4 different data structures to keep track of the things. So this is like pseudocode, but we are also going to describe like other ways to implement this. In those, like you might require some other data structures. But for now, for the sake of this worked example, we'll be dealing with 4 different data structures. 2 of them will be arrays and 2 of them will be sets. The first set is called set S, that will contain all the vertices for which we have already computed the shortest path. It's kind of similar to the vertices that we have marked or we have already visited, something like that. And initially, this set is going to be empty. Set V minus S is another data structure that will contain all the vertices that still need to be processed or for which we still haven't finished computing the shortest path. So in this case, V minus S will contain all the vertices for this graph, which include, like, they have 5 vertices, so they are from 0 to 4. So V minus S will contain the numbers 0, 1, 2, 3, and 4. Next, we have 2 different arrays. The first one is called DV and the second one is called PV. The size of both of these arrays is going to be equal to the number of vertices. Now, here in this graph on the right, you can see that the vertices are labeled 0, 1, 2, 3, 4 for the sake of simplicity or for the sake of worked example. But in reality, it could be any label, which it could be A, B, a string, or any object. So if that's the case, you might need another data structure to keep a track of mapping of like each of the vertex labels with an integer, because dv and pv are calculated based on that, so it will be easier to map those in that case. So dv is an array that contains the shortest distance from the source vertex to the vertex v. So here we have dv whose size is going to be 5 because there are 5 vertices. Now at each location, the value determines what is the shortest path between the source vertex and 1. So let's say for this graph, the source is 0. So 0 and 0 will return what is the shortest path between 0 and 0. 1 will return what is the shortest path from 0 to 1. 2 will return what's the shortest path between 0 to 2. And 3, what's the shortest path between 0 to 3, and so on. So every cell will store the shortest path between the source and that particular vertex. Next, we have another array that's called PV. This will contain the predecessor of P in the path from S to V. So I'll give you an example. Let's say if we have the shortest path from 0 to 1 as 10. So in this example, it's going to be 10 because all the other ones are going to be longer, as you can visually see. So at position 1, we will store what is its predecessor node to reach that path. So in this case, one's predecessor is 0, so 0 will be stored. Maybe it's not necessary that like let's say if it's a longer path from 0 to 1 to 3 to reach 3, we won't be storing 0 and 1. We'll just store the previous node, which is 1, and we'll see like how to maintain the path or how to calculate the path based on these data structures later on after we have finished the worked example. So initially, the dv vertex, the dv array, the distance array, is going to contain like we'll initialize the source at in the array to the value 0, and all other values will be infinity. PV will store all the previous paths. So initially we'll initialize that to -1. And at the end of the algorithm, let's say if any of our locations in PV is, if that's equal to -1, that means that there's like we cannot reach one vertex to another, which is there's no path to be reached from source to this vertex. So let's say if we had -1 at location 0, that means there's no path from 0 to to this vertex 0. In this case, it will remain -1 because there's no self loop. So if there was a self loop, then this should have been another value like 0. That's how it will look like. So let's see the complete example of how this is going to work. So initially we have the set S that contains no vertices. Then we have v minus h s, which we call like need processing set. Uh, so that contains all the vertices. This is like a table that stores v is basically referring to each of the vertex labels. So it's 0 to 4 in this case, and dv is the path, the shortest path between the source vertex and the label v. PV is again the predecessor of the shortest path that contains that will require us to reach to the vertex V. So initially we have this dv initialized to 0 for the source because our source in this case is 0. Let's say if this if we were computing it with the source 4, then the fourth location will have dv equal to 0 and everything else will be infinite. PVs, the predecessors, will be -1 when we start this algorithm. Now, one thing you want to note is like this data structure is actually our answer, which is dv at the end of the algorithm. Whatever values this algorithm gives us back, that's in the form of this dv and pv. And what this dv means is what is the shortest path that will be required to reach from 0 to 2, or from 0 to 1, from 0 to 3, and so on. So at the end of the algorithm, all the correct answers will be in this particular table. So let's start the algorithm. We start with the vertex that has the minimum distance in dv. So in this dv, we'll see what is the minimum value. So in this case, it's 0. So our start vertex is going to be this vertex 0. Okay. Another thing to note is, for the sake of simplicity, all these blue values here, I've just copied all the numbers in dv here because it's easier to calculate it once you are doing this in the exam, or like if you are just trying to practice these values. So these values here just are dvs, which are there in the table. Okay. So we start with the vertex that has minimum distance and we move that to computed, or we are still processing them. Next, what we are going to do is we are going to process each edge that is adjacent to this vertex 0. So let's say if we have the source vertex, what you're going to do is you're going to call the function get adjacent, which we already developed in the previous lectures. And then we are going to perform something called relaxation. So this idea of relaxation is central to almost all different graph algorithms that we are going to see, and it's going to reoccur again and again. So the idea behind relaxation is that, like, if we have a vertex that's called x, and its distance, like if the distance to that vertex is greater than the predecessor's distance plus the weight of the edge, that is from the predecessor to the current vertex, which is in this case this one, then we are going to swap the values of the distances, which is if you have the distance 0 and if you have edge weight as 10, you're going to sum these two up, which is 0 plus 10, and you're going to compare this with the current distance. So since this is greater, that means there's a shorter distance that is possible to reach that particular vertex from the source vertex. So we are just going to swap these values, which is uh, we'll cut this the distance, that the current shortest distance, and we are going to replace this with our previous vertex plus the edge weight, which is now it will be 10. Similarly, we'll change this in the table. So that's what we are going to do. And we are going to replace its predecessor, which is now instead of -1, the predecessor is going to be 0. So the entire algorithm is just this, which is we are just going to repeat this again and again till all our vertices are calculated or computed. So in this case, there were three edges. The first one was 10, the second one is 30. So 0 plus 30 is 30 is less than infinity. So we are going to delete this infinity, replace it with 30, replace it in our table, and change the vertex to 0. Next, we have this third edge that still needs to be processed. So we have 0 plus 100, and this 100 is less than infinity. So we are going to delete this infinite and replace this in the table with the predecessor vertex as 0. Okay, so this is just one iteration. We are processing all the edges one by one, and they can be processed in any order. It doesn't matter. Okay, so after the processing, you can see like we have changed three values here, which is we have now 10 and 0, 30 and 0, and 100 and 0. And we have updated these based on our relaxation. Now the S is computed and it's completed. Next, we are going to start with the next node, which is the least. So in this case, we are going to see which is the minimum value, and we cannot select the one that have already been computed. So these ones should not be selected. So in this case, we do not have this choice. So we just have these four choices. The least one is 10. So the next vertex that we are going to process is this vertex 1. Okay, so next we pick 1. We do the same step, which is we find out what are its adjacent edges in this case. So we have this one, then we have this one. So I think we have two of them, and you can see we have two of them. Next, what we are going to do is we are again going to perform the relaxation, which is now the relaxation won't be on the source, it will be from the current vertex. So it will be 10 plus 50. Now 60 is less than infinity. So we are going to replace the value of infinity on the vertex 2. So here at number 2, we'll change this to 60. The predecessor of 2 will now become 1 because the path is coming from number 1. Next, we are going to do that for the other one as well. Now 10 plus 50 is 60. 60 is in fact greater than 30, so we do not have to make any changes. So relaxation will not occur on steps which have greater, which have lesser path weights that are available to be reached from another vertex compared to like if you are trying from another vertex plus the weight, if that value is greater, you do not have to make the swap. So here, like if we go back to the relaxation step, you can see this value was not satisfied, so we are not going to relax it. And here you can see that from 1, uh, 1 second, I just lost. Yes. So from 1 to 3, this 60 value was greater. So we are going to we are not going to do anything from this. So here you can see the only one value changed from the previous one to this one, which is 60 and 1. So now we are done with 1. So we'll move 1 to this computed set. Next, we are now going to pick the minimum element in DV that has not been visited. So here 0 and 1 has already been visited. We have 3 choices. We are going to pick 3 because 30 is the next minimum. So we are going to pick this 31. Okay. Next, we are going to see again what are its adjacent vertices. So here it has 3 adjacent vertices. The first one is to 4, the other one is to 1, and the third one is to 2. So again, we are going to perform the relaxation. So we check the distance at vertex 3, which is 30. We add this to this number 10. Okay, so 30 plus 10 is 40. And since 40 is greater than 10, we don't do anything. Now again, we check it 30 plus 20. So 30 plus 20 is 50. Since 50 is less than 60, we are going to replace 60 with 50. Similarly, we are going to change that in the table. And now the predecessor of 2 node will become 3. We still have one more edge that we need to relax. So in this case, this edge is 30 plus 60, that's 90. And 90 is less than 100, so we are going to change these two numbers. So 100 will be replaced with 90, and the predecessor of 4 now becomes the node 3. So you can see like we have just changed the two values here in the table. We moved number 3 to processed, which is we have already computed this, and we repeat the process for the remaining elements of the set v minus s. So for the v minus s, we have just two choices now. Since the 50 is less than 90, we are going to pick this element, the number 2. So 2 is the next node that is going to be processed. We have like 50. There's only one edge that is a possibility from 2. So from 2, there's only one edge right here that goes to 4. You're going to sum these numbers up, which is 50 plus 10. This is 60, and since 60 is less than this number 90, we are going to cut 90 and replace it with 60 in the relaxation step. So it will be 60, and we change the value from 3 to 2 because that's the predecessor vertex. So now 2 is also done, so we move that to the computed set. We still have to process vertex 4. So in this case, we pick now 4 and we see what are its adjacent values. Since it doesn't have any adjacent values, we can stop our algorithm because there are no edges that need to be processed, and you can move 4 to the computed set. So we are now done. This table is now our answer, and how to read this table, I'm just going to show you now. So the shortest distance from 0 to 1 is 10 units, and the shortest distance from 0 to 0 is 0 units because uh, the like there's no path from that, and also like that question might never be asked. The next one is what is the shortest distance between 0 to 2? It's going to be 50. And what's the shortest distance between 0 to 3? That's going to be 30. And finally, what's the shortest distance between 0 to 4, which is 60. Now, what is the path? Like, let's say if somebody asks you, what is the path between 0 and 4? How you can calculate that is you go to the fourth index, like you start with the destination node, you see what's its predecessor that is in the table. So in this case, it's 2. Next, you go to the 2's position in the table. You see its predecessor is 3, so you append that. And finally, you go to 3 and you see its previous is 0. So now we have reached the source path, which is the source node was 0, and that's what we are trying to compute. So the path from 0 for from to reach the node 4 is going to be the reverse of this, which is it's going to be 0, 3, 2, and 4. So as you can see, like, let me just color this, which is 0 to 3, it's 30 units. Then 3 to 2, it's 20 units. So 30 plus 20 is 50. And then 2 to 4, like this one, is 10 units. So 50 plus 10 is 60. So you can see the total path was 60, and this is how we are going to reach it. Like, let's say if programmatically, if you are trying to calculate these paths, they are also pretty easy, because what you can do is you can store these numbers, the previous numbers, you push the destination node. So let's say if I want to find out what is the path from source to 4, you push the destination, which is 4, in the stack. You go to the stacks, like the position, the predecessor of the top of the stack, which is 4's predecessor. You push that, which is now it's going to be 2. Next, you are going to again, like, pop the pop, or just see what is on the top of the stack. You are going to see the predecessor of 2, push that. Again, you are going to see the what's on the top of the stack, see its predecessor, it's 0. And you are going to repeat this till the top of the stack matches the source. So it's I don't know if you will be implementing this or not, but if you implement it, use a stack, and if you pop the elements of the stack, that's going to give you the entire path from 0 to 4. So in this case, it's 0, 3, 2, and 4. So for the sake of the exam, you won't be asked like pseudocode, like write the pseudocode of Dijkstra, but you might be given some graphs, and you might be asked like what would these tables look like, or what could be the value at a particular step in this algorithm. But there's a stepping problem on Dijkstra's shortest path algorithm, and it's always good to like practice, maybe like do it in your free time to implement this algorithm. In the next video, like again, like path from 0 to 4 is 0, 3, 2, 4, as we calculated. In the next video, we are going to go over the pseudocode of what we just did, as well as I'm going to show you one other pseudocode uh, that is actually used to implement this algorithm. Thank you.